Welcome everyone. I am Vinay Kumar and I'm a senior scientist at VTT, and I am going to share with you today our journey that we took in development of these bio-based packaging materials from lab to pilot, because these were novel materials. They required some special processing parameters and also special techniques for characterization, etc. And that's why we wanted to share with you our learnings when we took these materials from lab to piloting. And of course, I was not alone in this journey. I was helped by uh, our team of researchers and also our experts who were guiding us in this. And our target food product group was actually confectionery. And in this current year, we are also planning to develop new materials for meat packaging as well. But in this particular presentation, I'm going to talk about confectionery food product group. So we had chocolate and cookies, and we were looking at the typical requirements for this kind of packaging, especially when it comes to barrier function. And we were looking at potential water vapor transmission rate of less than 5 gram per meter square per day and oxygen transmission rate of less than 2. And of course, these requirements can vary a little bit depending on what product you are packing. So these were the targets that we had kind of set for ourselves with our new packaging materials. We wanted to see how close we can get to these targets. And this is a brief slide highlighting our development plan for these materials. And if we look at the left side, where we have these packaging structures, we had two types. One packaging structure had a moisture barrier layer, oxygen barrier layer, and another moisture barrier layer. And this was a transparent or a translucent film, which was used as a package window or a lid. This package design that you see here, this is just for uh, showing you where these different parts were used. We did not actually make this type of package. Then the other packaging structure was similar to this, except that we also had a waste paper involved in that. And that was the main package structure. So the main package structure was built of this. And then if we had a window or a lid, then this could be used for that. And the materials that we used for this development were all bio-based and biodegradable. We have studied their biodegradability, and we have kind of ensured that the materials we are working with are biodegradable in soil and marine conditions. And we used different paper grades in lab, but on the pilot, we had decided to go with one particular paper grade. For moisture barrier, we had two options. One was bio-PBSA and the other one was modified PLA. For oxygen barrier, we had fibrillated cellulose. You can call it microfibrillated cellulose or cellulose microfibers. And then we had the other moisture barrier layer, which was again either bio-PBSA or PLUX. And the target food product group, as I mentioned already, was confectionery products. And the technologies that we used for producing these multi-layer structures, they covered basically two main technologies: dispersion coating and the extrusion coating or film production. And for fibrillated cellulose, we also used cast coating method to apply slightly thicker layers where needed. And if we go to the lab studies part, so we can look at the structure development here, for example, for extrusion-based structure, where we were using this bio-PBSA because this film or coating was produced using extrusion technology. So we started with paper, extrusion coated that with bio-PBSA, and then we applied a dispersion coating of fibrillated cellulose on top of the bio-PBSA. And in the lab, of course, we could not take this to another extrusion coating step. So we basically laminated the same bio-PBSA coated paper upside down on that. And then this was characterized for barrier performance. Same route was followed for dispersion based structure, where we coated the flux dispersion on paper using dispersion coating. Then fibrillated cellulose was applied on top of flux coating using dispersion coating, and then we applied another layer of flux on top of that. So this was a slightly simpler structure to produce in lab compared to this one. And if we look at the barrier results for these, so for the extrusion-based structure where we have paper bio-PBSA and fibrillated cellulose combination, so you can see that water vapor transmission rate for only the bio-PBSA coated paper was around 63. Of course, bio-PBSA was contributing to that barrier, but then when we had the full structure, we were able to bring it down to around 15. So this was a good improvement compared to just the bio-PBSA coated paper. Then the oxygen transmission rate is interesting because here we were almost above the measurement limit, and the final structure with this fibrillated cellulose coating acting as an oxygen barrier layer, we were able to bring it down to 1, which is within our target that we had set out in the beginning. For dispersion-based structure as well, just for the paper, we had a water vapor transmission rate of 250, and with the flux fibrillated cellulose and flux coating structure, we brought it down to 6.7, which was also really good improvement. And for oxygen transmission rate, again, we were able to bring the OTR value significantly down. Of course, it was not as good as this structure because our flux dispersion coating was destroying a little bit of this fibrillated cellulose coating because both are water dispersions. So that's why we got a slightly poor barrier here. But anyway, these results were exciting for us to take these structures to piloting and see whether we can replicate these results on pilot or there will be any challenges when we try to work with these materials on the pilot line. For piloting purposes, we were using two of our VTT pilot lines. One is called SUTCO, Surface Treatment Concept Line. This is based in Espoo, and this is a modular pilot line for aqueous coatings. Here you can see a picture of the line. And on this line, we were performing all our dispersion or cast coatings. And then we have a Plasco line, which is in Tampere. And in this line, we were using cast film or extrusion coating processes. And here you can see a picture of the line. And this was used for basically bio-PBSA film extrusion and coating work. So for production of structure 1, which was extrusion based, as we saw on the first slide. So we had a bio-PBSA film produced on the Plasco line first, and then it was sent to our VTT SUTCO pilot line in Espoo, and we applied this fibrillated cellulose coating on top of this bio-PBSA film, and then it was sent back to Tampere pilot line, and we basically applied another layer of this bio-PBSA on top of that structure. And in this structure, we had around 40 GSM of bio-PBSA on both sides, and the fibrillated cellulose coating was around 8 GSM. So this was the full structure produced on pilot. Of course, we faced some challenges when we were producing this structure. For example, this bio-PBSA is a new polymer, and of course, the extrusion line had to be really adjusted. The parameters needed to be adjusted so that we could get a good quality film and coating. And of course, the coating of fibrillated cellulose was also not so straightforward because when you are drying it online, you need to really be careful with the temperature settings that you are using. So there were challenges, but we anyway managed to produce this structure on the pilot. And then comes the extrusion-based structure 2, where we had paper as well. And here we had to actually also use primer coating for attaching this bio-PBSA to paper. And this was observed during the lab trial as well, that the bio-PBSA was not sticking so well to paper. And that's why we used a very thin primer layer to ensure this adhesion. Surprisingly, the fibrillated cellulose coating was adhering pretty well to bio-PBSA. Although one would not maybe expect that, because when it's not sticking to paper, it might have issues here as well. But the adhesion was much better here. I would not say perfect, but it was much better with fibrillated cellulose than paper. And this structure was again reduced in a similar manner on Plasco, extrusion coating of paper with bio-PBSA, on Sutcopilot, fibrillated cellulose coating, and then again on Plasco bio-PBSA coating. And these were the GSMs of these different layers. You can see some pictures of this process of production here. And then the dispersion-based structure was actually produced on the Sutcopilot line, because there we did not have to use extrusion coating technology at all. So we started with our base paper, applied the flux dispersion, which was around 15 GSM coating layer, and then applied fibrillated cellulose coating on top of that, around 8 GSM again. And on top of that, after drying, we applied 15 GSM of flux coating. And here you can see actually the 3 layers on the paper. So the first flux layer, then in this one here we have the fibrillated cellulose coating, and then we have flux layer on top again. Looking at the characterization data for these particular structures that were produced on pilot. So for the extrusion structure, now you can see that because we are able to also measure the water vapor transmission rate of just the base paper, which was around 302. For the full structure, we were able to bring it down to around 30. This is not as good as we saw in the lab, but I think this needs a little bit of optimization in terms of how much material was applied as coating, and there might be some defects during the pilot production as well, which would of course need a bit of fixing. Same was observed with the paper-based structure, that we were able to bring it down to around 50. Not as good as in the lab, but still a reasonable barrier compared to the base paper that we had started with. Oxygen barrier, again, here we are getting the same improvement. So the substrate was above the detection limit or above the measurement limit. And then the final structure, we were able to get oxygen barrier of 1.45. So this was an excellent result. So this structure was basically performing as we were expecting it to. Then the OTR for paper-based structure, here we are seeing a good improvement, but of course it's not as good as this structure. And the reason for this was that when we had the base paper in picture, we might have used slightly higher temperatures for drying this coating. And what that caused was that there were some micro cracks in the coating post drying, and those might have caused some of this slightly poorer barrier compared to this one. But that is something that is fixable, and we can potentially get to value of 1 for this structure too. Dispersion structure, we faced some challenges, especially with the OTR. For example, you can see that, of course, we are getting a good water vapor transmission rate reduction, but then the OTR is not good at all. And here, the problem was caused by the top layer application flux coating, which was, of course, a water-based dispersion. And it was, when it was done in the lab, the fibrillated cellulose coating might have been actually thicker. On pilot line, we had to reduce the thickness because of the drying requirements. And in the lab, that thick coating could withstand the top coating application. But on the pilot, since it was not thick enough, so this got destroyed completely when we applied the flux coating. So our way forward for this is that we want to increase the thickness of this coating in our next pilot, so that this total destruction does not happen. Or if we could apply them in one go, for example, using a curtain coating technology, that would be a perfect solution. And we also looked at the basic techno-economic of these bio-based packaging structures. Please keep in mind that these values are calculated just on the material costs. So these do not consider the, let's say, operational expenditure when it comes to running the machines or drying and all that, but just considering the basic material costs. And also there you can see that there is a variation here, and this is because we have tried to get these price estimates from different sources. So that's why there is a bit of variation in the price levels. But what's interesting here is that flux structure, for instance, which is dispersion-based structure, it is actually able to compete in price with the plastic-based packaging structure that we have here. The extrusion structure 1 and 2, they are slightly higher in price, but I have a feeling that if we are able to optimize these material amounts for different layers, we could also get these potentially to be able to compete with the plastic structure. Also, we need to keep in mind that these are not the industrial quantities prices. Basically, when you get these materials for piloting, you are getting them at much higher prices compared to let's say industrial scale production. So that is another reason for these slightly higher values. Then, of course, when we had produced these structures, we wanted to produce demo packages and kind of wanted to study their performance as a package and also look at the shelf life. And what's interesting here is that with these new materials, the sealing conditions are actually right within the range of industrial practices. We might want to reduce the time of the sealing, but other parameters are, I think, well within the range. And here you can see 2 examples of the packages that we had produced, and these are fully bio-based, recyclable, and marine biodegradable materials. And we have got quite reasonable barrier performance from these, good heat sealing, as well as the good performance in terms of mechanical integrity. We still are waiting for the shelf life results, so let's hope that those are also on the positive side. Just to summarize, we were able to demonstrate the upscaling of these new bio-based and biodegradable packaging material solutions from lab to pilot. Of course, we faced challenges. It was not so straightforward to work with these materials. We had to optimize various process parameters in order to accommodate these materials. And then these demo materials were actually used for packaging chocolates and cookies. We are still waiting for the shelf life test results, and we are planning to revisit the piloting of dispersion structure, as I already mentioned that we might have destroyed the fibrillated cellulose coating because we could see this poor barrier of oxygen. So we are planning to redo that with slightly thicker fibrillated cellulose coating layer, and that way able to reach the target barrier. And this work kind of demonstrates that with these new materials, we are able to go to a larger production scale. Material and process optimization will be needed, but it is indeed possible to work with these materials in large scale. And these novel materials can be cost competitive as well if we upscale their production to larger quantities. And we feel that the cost is actually not very far from the existing solutions. With that, I would like to thank you all for being here. And if you have any questions, I'll be happy to answer. Thank you.
Thank you, Vinay. We have here questions for you in the chat. I'll read the first one. What is the added value of paper in this case? Paper production is very heavy burden for the environment.
Yes, Kirsi, that's a very good question. Actually, after we saw these results, we were ourselves also feeling that just the bio-PBSA fibrillated cellulose bio-PBSA structure itself might be enough. But if we want to go with the dispersion coating technologies, then we do need a base to work with. For example, flux we could not basically apply on anything else than paper. You might start with a bio-based plastic for that matter to apply the fibrillated cellulose coating. But then we are talking about two different materials again. So I think paper has its role here, but when it comes to the performance and the minimum material requirement, I think this bio-PBSA fibrillated cellulose bio-PBSA structure is the best in terms of the least material amount and the best performance.
Yes, thank you, Vinay. Then other question, if bio-based layer have thickness 70 to 100 micrometers, there are no possibilities against barrier polymers or SEOX or aluminium 203 coating with 1 to 10 micrometers. How do you answer to this?
Yes, so the oxygen barrier layer that we have here is actually quite thin. In fact, I would say that we have applied higher thickness of that layer than required because we can get good barrier performance even with lower thickness of that. But other material layers, for example, the moisture barrier that we have is well within the range of normal polymer films. We are not very far off there. Of course, as I mentioned during the presentation, these material layers are not really optimized for the amounts because here we wanted to show a proof of concept with the right amount. We are not, we have not used 100 microns thick layers. We are still in a reasonable range. But I would say that if these were to be optimized properly, we can reduce the thicknesses of the layers and still get the performance.
Thank you. Then why PLA was selected as a biopolymer?
So PLA has actually been around for quite a while, and it has been known for good water vapor barrier. But what was most interesting for us was the possibility to use the dispersion coating technology, because that's quite standard industrial process, and it allows us to apply much thinner layers as well if needed. And then we have a special modification of PLA, which has made it biodegradable, let's say more easily biodegradable.
Yes.
And still maintaining the performance of barrier.
Yeah.
So that was one of the, let's say, main motivation, that if we have the material which can biodegrade quickly and still get the barrier, why not try it?
Yeah. So I want to emphasize that it's not PLA, it's modified PLA. It's not PLA polymer. Totally different polymer, but the basic for the modification of PLA. Okay, thank you, Vinay. Then do we have still? Yes. Do you think it will be possible to decrease the grammage of the paper later as the structure will be optimized?
Yes. So especially for the bio-PBSA structure, I think one can work with much low grammage paper. I think the reason we selected this 90 GSM paper was mostly because of the dispersion coating layer, because there on the machine we were a bit limited in terms of how we could handle a thin paper. So that's why we wanted to be on safer side. But for the extrusion coating, I think we can work with, let's say, even 40 GSM or lower GSM paper if needed. But I think here the main target was to keep it suitable for dispersion coating process.
Yes, and then still are paper-based constructions suitable for paper recycling?
I think we are actually now looking at the recyclability of these structures. We have sent them for these repulping studies. Especially the dispersion coated structure is fully repulpable. At least that's what we have seen in our initial results. But the bio-PBSA coated structure, it's biodegradable. But how repulpable is that is still an open question. I think we would have to look into that.
But anyway, the aim is that the package must be recyclable in paper or board fraction. And yeah, okay.
And
Then
Kirsi, there is actually one hand. I was thinking, should we take that? Because yeah, he has been waiting. And Vinay, there are probably some questions you haven't replied, but if you can reply on the chat.
Yes, I can go to the chat and reply.
Yes.
Yeah, and we take this one question before we have a break.
Yeah, so hello everyone, this is Erkki Laiti, and thank you Kumar for the excellent and interesting presentation. One question that occurred to me was the actual resistance to folding and crack resistance and resistance to converting. Did you have that kind of a collection of data that you looked if the barrier properties were kept when the samples were folded, for example?
Yes, Erkki, that's a very good comment, and we are now actually preparing a manuscript for this, where we are planning to look at that particular data, so that we will be basically folding them and seeing if the barrier is maintained after folding. One thing that we have looked at is if we try to, let's say, stretch the layer, of course not breaking it all the way, but a little bit of stretch, and seeing the barrier performance as a function of that stretch. That we have looked at, and we have seen that if you don't crack the fibrillated cellulose layer, then you can still maintain the barrier, but only up to an extent, because fibrillated cellulose coating layer is the most fragile one in this whole structure. So if you end up basically breaking that, then your oxygen barrier suffers. The other layers are quite okay. For example, the folding could be easily managed with the bio-PBSA layers and also with flux layers. So my only concern would be the fibrillated cellulose coating part. So if that can be somehow, if that can handle it, then we are good with the structure. So we will be looking at that data.
Okay.
Thank you.